Ladies and gentlemen, good evening for Jakarta time, good afternoon in Middle East, and good morning in US, or good afternoon in Europe, and all everybody. I think we are very happy tonight because ISPG and SPE Java section, basically we can make a webinar session 3. So today we have a special guest, which is very famous in Petrophysics world. We have Mr. Charles Richard Smart. Usually I call him Chris Smart. So as you know that during COVID pandemic 19, normally ISPG, which stand for Indonesian Society of Petroleum Geologists, and in collaboration with SPE Java section, we conduct a webinar sharing session, basically to elevate all the sharing session from the expert, from the industry to the society. And tonight we have a topics about multi-phase flow petrophysics. And again, on behalf of SPE and ISPG, I would like to say thanks to Chris for your willingness to share our knowledge related carbonate petrophysics. And later maybe you will explore and in more detail. And for your information, tonight our discussion will be led by Mas Akbar as a moderator. So later he will introduce our speaker and lead the discussion. And I think that's it. Again, I would like to say thanks to all participants who can join tonight in Indonesian time. Hopefully you can get something from this event. And congratulations for all of us. Mas Akbar, time for you.
Okay, thank you, Bang Joyanta. So this is Akbar speaking from Budapest, Hungary. So thank you very much, Mr. Charles Richard Smart or Mr. Chris Smart. We are so glad having you here for the discussion tonight. So on behalf of SPG and SPE, I would lead this discussion today for the webinar session 3 about the multi-phase flow petrophysics, physics-based approach for deriving SW from NMR and the formation sampling in low resistivity carbonates. So before Mr. Chris starting his presentation, let me introduce him a bit about his experience. So he is now a senior petrophysicist or leading the petrophysics study in the Baker Hughes International in Abu Dhabi. He already 7 years working there, but he also has a various experience in the oil companies, working in the various projects in around the world. And also he works also as a consultant as well. And for his education background, he graduated from Virginia Polytechnic Institute and State University for a Master of Science in Nuclear Science and Engineering. While for the Bachelor of Science, he was graduated from Virginia Military in Physics. He also chosen for the many kind of awards in SPWLA, distinguished lectures, and also from various rewards in oil companies such as BP or Amoco, even in various conference in SPWLA. So, Mr. Charles, let's start your presentations. We are very happy having you tonight. So for the rule for the presentation today, it will be around 2 hours. 1 hour will be presenting by Mr. Chris, and after next 1 hour, it will be start with the discussions. So for Mr. Chris, time is yours.
Chris, you can share a screen. Chris, maybe you can unmute.
I'm unmuted, I believe. Is that correct?
Yeah, it's clear.
Okay.
Yes.
Okay, sorry. Let me start over again. Ramadan Kareem to the
Ramadan
world.
Kareem.
Kareem.
This presentation was put together for the ISPG Low Resistivity Pay Conference this past fall in Muscat. We were one of the few participants that came with solutions for carbonates, as most of the information in application for low resistivity pay seems to be in sandstones. I would like to recognize my collaborators, and this whole idea of multi-phase petrophysics has its heart in Saudi Arabia with Ed Clark, Jan Bunting, Greg Phillips, and my partner in crime, Nicholas Sewer, when he was with the kingdom. This methodology that you're going to see today is
Chris,
intended to
sorry.
Mr. Chris, sorry for
Hello.
interruption.
Yes.
Could you please to share your presentations?
Maybe that's in the second screen.
New share.
You shared your screen in the different screen, I think.
Maybe it calls it number 2 now. Okay. Okay, that should be the title screen. Is that correct?
It's not yet. It's still your POF.
Not yet, sir.
You may have to stop sharing and then go to your PowerPoint and then share again.
Okay, I'll stop sharing. And then I will close the presentation. And then, let's see, I have to go to start share. Yeah, I see it. Share screen. Should be screen number 3. Do you see screen number 3?
Yeah, we see your screen, but this is showing the Explorer, your folder Explorer, not the presentations.
That's what's wrong with having 3 screens. It should be screen number 3.
Release of files.
Why don't you try to share a window instead of sharing your screen? Do you have that option?
Do I have that option? I will find out.
We can
This
see
looks
it, Chris.
better. It's working now, I think.
It is working. Let me see if the presentation goes full screen. Can you see
Yes.
collaborating
Yes.
colleagues? Okay.
That's perfect.
The full physics model is derived from Saudi Aramco. And the guys who were instrumental in doing that since about 2000 were Ed Clark, Jan Bunting, Greg Phillips, and then Nicholas Sewer. Now, I was bright enough to hire Nicholas about 4 years ago to Baker as one of the smart young And I've also had the privilege of working with Oliver Monkey up in our Cella office. And I will point out most of this full physics is all Nicholas, every bit of it. There are a lot of contributions that I've made, and Oliver has made significant advancements also. This is all background, and we'll go into a little background slide. Any pore geometry work that you do with mercury is based upon Bert Tamir's representation of the mercury experiment. And he determined that you could describe a very complicated mercury experiment by the use of what he calls the Tamir hyperbola. There are two asymptotes, one being the core volume, BV, infinity, and the entry pressure. Now, the shape of the Tamir hyperbola is related to what's called the G factor. And this is statistically tells you how dissimilar or similar or dissimilar the pore throat systems are in your pore geometry. The smaller the G, the tighter the response. The bigger the G, the more difference you have in the pore geometry. Now, the other beauty about Tamir is that you can model very complicated capillary pressure experiments because the Tamir hyperbola works with the principle of superposition. So you can have multiple pore geometries present in a rock system and be able to very accurately describe it. Now, the second part of this is the saturation height solve. And we assume that in the first approximation that the brine density and the hydrocarbon densities are going to be consistent through the entire column that you're investigating. And we also assume that these fluids are immiscible with each other. We need to be able to calibrate the mercury saturation to Dean Stark. And we do this by modifying by understanding what the contact is, the height above free water, and the conversion from laboratory mercury saturation to the equivalent reservoir saturation using percent. And then we will investigate using porosity, permeability, and height above contact, and knowing what the pore geometry is at each depth level within your interval of investigation to derive a hydrocarbon saturation. And the paper index at the bottom, I'm going to bloody detail how to go from A to B to C to Z.
Chris, interruption. Can you make make your microphone closer?
Yeah, I got it as close as I can get it.
Okay.
On my lips. I hope that works. So the basic problem is that we have a misconception that the value of water saturation has a correlation, a strong correlation to producibility into a well. And there are a lot of false negatives. And that's why you're going to have a talk tomorrow about working sandstones, and I'm talking today about carbonates. It's false negatives. Now, in the Middle East, and this talk was focused around Middle Eastern carbonates, we have a unique situation. We have extremely high salinity formations, and we have high capillarity, so there's a large waste zone and significant surface conduction. Now, there's been a whole lot of different techniques to try to fix resistivity, fix arching parameters. Let's try using different experiments like Dean Stark from core. Let's use capillary pressure. Let's use sigma, azimuthal resistivity, dual wait time, NMR, etc. We'll do
multi-physics for looking at complex mineralogy, looking at differences in water and gas, water, oil, and gas. So we can do all the work that we want to do with formation evaluation. Now, a lot, especially today, everybody's going cheap or went cheap probably about 10 years ago. And with the number of directional wells, a lot of this is boiled down to getting porosity right using LWD and getting and try to use, we like to use NMR to get some contextual data about the pore system. And then we have evolved into this multi-phase petrophysics, which we're going to talk about today, where we're going to try to de-risk fluid typing, compartmentalization, calibrating multi-flow, multi-phase producibility, and permeability. So without much ado, we'll go into where does low resistivity pay show up in the Middle East. It's the areas that I have shaded green are areas that have profound low resistivity pay intervals. Now, the interesting part about this, at least in the Middle East, you may find examples from your region, but most of the low resistivity pay almost all of it's associated with micrites. We don't have many chalks here, but chalk and micrite are from the same beastie. But in addition, most of the low resistivity paying carbonates in the Middle East are in the Cretaceous formation. There's a lot of Jurassic carbonates, and there's a lot of huge reservoirs in the Jurassic, but the bulk of these are conventional pays. So we'll move on. Now, a colleague of mine, Ed Pittman at Amoco, and George Asquith looked into the problems with low resistivity pay, and specifically in carbonates, and it basically comes down to pore geometry and the contrast between salinity and the high conductivity of the brine phase. And almost every one of the low resistivity pays in carbonates are profoundly water wet rocks. So you've got a short circuit in your rock system. And we'll look at different suggestions for what call low resistivity pay. And in carbonates, it basically boils down to microcrystalline carbonate, micrites, and chalks, and high capillarity. So what you basically have is your pore system. You run your current flow for your resistivity tool through there, and it ignores the hydrocarbon. The contrast between the brine and the hydrocarbon non-conductivity is so awesome that unless you have a continuous phase of hydrocarbons, you are reluctantly going to see them in the analytical results. Now, here's a photomicrograph of common micrite. These grains are on the order of 10 to, or actually several microns to 10 microns. Now, the interesting thing about micrites is that they are exceptionally monomodal. They are very hyperbolic in their response. And the plot, this is a plot of porosity and permeability from WAR, where Ed in 2005 published his seminal work, the Rosetta Stone. In yellow, I have identified this is the micrite trend, and you'll notice that only right here we're at 1 millidarcy, and most of your micrites are less than 40 millidarcies. Now, Your micrite is a very bland looking rock. You don't see a lot of visible porosity, and it follows that trend that you saw in yellow. Now, the bioclastics sediments, it shows up in the high perm intervals, and that's because the permeability in a pore system is proportional to the pore throat radius. And so in Guar, which is the world's largest reservoir, you see 4 decades or more of permeability for the same porosity. And so what you're seeing is a difference in pore geometry, with the pore geometry quality increasing as you go up in permeability, and the pore throat size gets huge. Now, also you get to see the bioclastic rocks. You see the impact of multimodality. The low capillary pressure that you see on entry pressure is coming from the large pore systems, but you almost always have a micritic component. So once you get high in reservoir, you're going to see a step change in saturation just due to pushing hydrocarbons into a pore system once you've filled up the big pores. Now, your micropore system, on the other hand, a very small change in capillary pressure makes a profound change in saturation. Now this particular sample is down here from a couple of PU, so it's not high quality rock. You would expect this to be under 0.01 millidarcies. But up in here, when you get up towards 10 to 20 millidarcies, some of your micrites may require 75 feet of column height, and within the next 25 to 50 feet of column height, you'll go from 100% water saturation to single digit. And that's the impact of the small g and high capillarity on the pore system, and why you can be very highly confused in carbonates. Now, we're going to break this talk into 2 components. The first component is the simple technique, which is basically using NMR formation testing to, along with capillary pressure and Buckles Leverett, to come up with a solution. So without much ado, we'll go to that, and we're going to make some assumptions. We're going to say that the T2 distribution can be transformed into a saturation distribution. Okay. And then Petrophysics. We're going to use NMR. We're going to use MICP, capillary pressure data, formation testing information, not only just pressures, but also sampling information so that we can know what the fraction flow is. Marry this with the capillary pressure data, go through Buckles Leverett to come with the fraction flow, and compare the answers. Okay. T2 distribution. This is the kind of answer product that you would see from NMR results. From your resistivity, and you're going to be looking at bulk volume oil plots. I know most of you are used to looking at bulk volume water. I believe in capillary pressure. The green volume would be the volume of porosity that's filled with hydrocarbons in the pore system, whereas the total porosity is the outside of this. The blue volume would be the volume of water. Then here's your NMR porosity. Now, our inputs are only going to be the fluid densities, your hydrocarbon and brine density, your best guess at the free water level, and information about wettability. And we're going to assume that you're dealing in the interval of interest, that you're going to be dealing with a monomodal micritic
pore system. And it's got limited pore architectural heterogeneity. For the most part, micrites are very, very strongly ordered unless you have a significant solution or dissolution porosity. Or, as you might see up here, you may actually have some bioclasts up in this portion of the reservoir. Now, these assumptions are usually quite valid if the permeability is under 10 to 20 millidarcies. That's a good place to start. And we're going to use Poiseuille's bundle of tube model to do the capillary height. And we're going to assume also that we have equilibrium between your capillary and buoyancy forces. Otherwise, the reservoir is static. So here's our log suite, our resistivity, our porosities, our initial Archie solution, and our NMR. We're going to use formation testing and do a Coates-Tamir because we probably don't have a lot of capillary pressure data from this exploration well. So we're going to use Coates-Tamir permeability, which has been normalized to the mobility from the formation tester. And then we're going to figure out where we put SO into the and when you have picked your correct PC0, you're going to see the increase in dark green is the increase in oil saturation due to the capillary effects from the micrite. So the light green is your original solution. The dark green is the added hydrocarbon volume. And where is that hydrocarbon in the pore system? The blues highlighted intervals have water in the pore system, and green is where your oil is positioned. Now, how do we do this? We're going to assume some pore heterogeneity, and that the T2 distribution, the width of the T2 distribution is analogous to the pore throat heterogeneity. So if you have a very narrow T2 distribution, you've got very homogeneous reservoir, very tightly ordered reservoir. So there's not a lot of diversity in your pore throat system. And so we're going to assume that there's a correlation between, that you can make a correlation between T2, your delta T2 distribution, and the Tamir G. And that additionally, that there's going to be a relationship between the T2 distribution and your inverse Corey exponent for your relative perm. And the Poiseuille PD can be derived from Poiseuille relationship, and Bunting and Clerk published this in from our buoyancy capillary forces, we can use the Tamir relationship to come up with a oil saturation as a function of porosity, the G shape factor, and your entry pressure based against your height from your free water contact. And when we combine these three things together, we will assume some uncertainty with our parameter selection, and we use Monte Carlo simulation to come up with a solution. And so we blew up this interval here on the analysis. And so we will get, here's our perm that we've transformed. Here's our uncertainty probability density function around oil saturation. Here is SO with our P50, P10, and P90. And then where did we put the oil in the NMR porosity distribution? Okay, so that was the first method. That was plain simple. Now, the second method is going to be the multi-phase flow petrophysics. Now, those of you who are working in sandstones, this technique will work in sandstones also, and especially applicable in arcosic sandstones. Now, I don't advise using it necessarily in thin bedded sandstones, but your massively bedded sandstones will do an excellent job. And I don't know where that line came from. I have no claim to this line. Okay, so it's a three-step approach. There's a machine learning bit, saturation height function, and tie to land, and then the Buckley-Leverett so that we end up with fractional flow. So in the machine learning, we're going to start in the porosity and perm envelope. So we will start with known core data. So here is nominally our mercury in micrite environment in at least guar. But we will take every single one of these points is a RCA plug where we've got porosity and permeability measured, and we've also got MICP measured on exactly the same plug that had porosity and permeability measured. And it's going to be a full 1-inch right-hand cylinder. Now, we'll add to that the MICP, and here's the first component of machine learning. This mercury experiment has 3 modes of porosity. The mode here on the right is the best pore system in your rock. Here's your second pore system. Here's your third pore system. And we use global nonlinear optimization, which is a very fast technique, and we can get about a 90% perfect solution in very short order. In this case, the experiment, we did 1,875 mercury experiments in 10 minutes. And so we end up with 3 mercury curves. Our best mercury curve, which is this one, for our first pore system, our second pore system, and our third pore system. And when we put them back together through the principle of superposition, we have replicated the mercury experiment very handily. Now, the next thing that we're going to do with the machine learning is we're going to take the porosity, the permeability, and the solutions from the Tamir deconvolution. How many modes do you have? What is your entry pressure, your bulk volume, and your G for each of your determined modes of of pore system in that rock sample? And so we're going to be able to use Gaussian process regression to be able to assume that there's a little bit of noise on our data, and that with inputs of porosity and permeability and a height position, we can investigate the mercury. We can investigate with using machine learning to derive the pore geometry architecture. And then we put this knowledge back into our solver, where we use inputs of your hydrocarbon and brine density, your first guess at free water level, and your interfacial tension contact angle. Once you've got that in, then we can, through the interval of interest, solve for your critical water saturation and your water saturation, and use land to be able to
determine where you are in imbibition and or drainage. Now, we've got saturation, we've got SOR, we've got critical water saturation. Now we can enter into Buckley-Leverett and predict the relative permeability and the phase behavior of the fluid. And ostensibly, your output that you're solving for is the fractional flow at every position in the interval of interest. Well, you're probably going to be wrong. But so your relationship, you're going to get a fractional flow curve based on KRO and KRW. And then depending, we enter into the fractional flow curve. And depending on whether you're in imbibition or drainage, I'm sorry, that's, never mind, we'll continue on. So based on the formation testing sampling result, you can use that to tune the model. And you can also sense check other information such as gas chromatography, UV fluorescence, your Archie saturation, and maybe if you've got core across the interval, Dean Stark. So I believe Dean Stark, it's volumetric, and compare it back. So at the end, your biggest uncertainty is going to be on what your free water level is. You can also introduce uncertainties associated with your Corey exponents, your maybe nonlinearity in your hydrocarbon density or your brine densities, any of the other parameters in there, and we will minimize a solution. And let's see how we do this. Okay, the first example here, and we're going to match the fractional flow from formation sampling, and we're going to honor the SW deflection from Archie. And so here's your result. You're seeing it change and where the iterations are going. In white here, you've got, and we see it change. The light green is the additional water saturation that or additional oil saturation that we've added to the reservoir. Here's our fractional flow. This is almost all oil, and we're almost all, we have just a little bit of water or oil down here, which probably came from a little bit green or something. But that's the first example. The second example, we're going to try to honor an SW deflection despite this interval being residual oils in it. So here we are again showing the different realizations of different height relationships for picking the PC0. Here we're testing just a little bit of oil, all water, increasing oil content, and so our resulting water saturation is here. And here is the SO that we get from, this is the total oil volume in that part of the pore system. Significantly higher reserve content. And then the last one is trying to honor an oil down tube. Same techniques. We search up and search down. We didn't get deep enough in the drilling process to get all the hydrocarbons. We get some cut here, and we can bring our contact deeper than the well is and establish where the PC0 is in the well. I'll show you one more example, and this is taking where we go with integrating to Swanson. And this was the the big improvement we've made in the last few years in the multi-physics. If you had to wait for your answers to come up with a solution, then you really couldn't integrate in the operational aspects of doing the fluid sampling on the exploration. So B.F. Swanson, who was a colleague of Bert Tamir back in 1960, proposed that, hey, this inflection point on the Tamir hyperbola can be related to permeability. And so Bert Swanson called this his apex point, and that's just the ratio of the mercury saturation divided by PC, and that raised to a power times 399 will be highly correlative to air pressure. Now, the other nice thing, and the core industry has taken this into the wing, so they take the apex point and get the pressure for that apex point, and that correlates. The PC for that apex point can be converted from capillary pressure to pore throat size, and that becomes the mean pore throat diameter for your primary pore system in your rock system. And that is very handy. Now, we took that, I challenged Nicholas, who's a very smart lad, to say, hey, we need to have this as an analytical result. So his first order approximation was this equation, where the PC, the capillary pressure for the apex point is 2 PD1 e to the minus square root of G1 over 2. Here's the proof of the pudding. Here is the analytical apex computation from the mercury analysis, and here is the result from the numerical solution, and there is the equation. So the result is we can get at any time a solution based on a pick of your PC0, which in this case would be down here. Here's your fractional flow solution. Here's your Tamir relationship. And this is a well with 2 intervals. Now I'm going to blow up the bottommost interval to show you how valuable this apex work is. The very left-hand portion of this is PD1. That's the entry pressure. The outside is the Swanson apex pressure. Now, in between, in this yellow here, that is the operating interval between first oil to last water. So there you have defined your transition zone in pressure. Now, you can have this computation done before you ever go in the hole with your, especially in wireline. There's usually 12 to 24 hours before you make a trip in the hole with a sampling tool. And so you can come up with the Tamir solutions for your well, and you can make guesstimates on where your free water level is based on your estimates on free water level based on maybe your structural closure, for example. And then go to pick intervals, and I've shaded it in green. These intervals that are highlighted in green are intervals that you would probably test dry hydrocarbons. Now, here is an operational technique which can save you hundreds of thousands of dollars of operating time by identifying the correct places to do your sample based on your next. And we're almost at the end, ladies and gentlemen. Here's the wrap up, and I'll let you guys read it. For, low resistivity pay, and then here's the takeaways that I want you to have. There is no foolproof logging solution. You've got to know your rock pores and fluids. You've got to understand your pore systems. But we've shown you at least two mechanisms to be able to drive uncertainty out of the solution. What we've shown you is a physics-derived model, and water saturation does not guarantee producibility. And we want to show you the value of NMR information sample. Now, that was it. And I no longer work for Baker Hughes, but Nicholas does. So if you have direct questions of somebody who might be able to do this kind of work for you, you can use this, take a picture of that screen, and you can get in touch with Nicholas by email, or you can get in touch with me. I answer the phone, I answer emails, and most of what I do is free because I don't work for anybody right now. So I'll give you my honest opinion and point you in the directions of people that can help you. Now, this where we need to go in the full physics. Right now, we can use the full physics model to get porosity, permeability, saturation. We can give you relative permeability. Now, we can also, the next step is to put in completions and nodal analysis and performance modeling, perforation performance modeling, so that you can predict what your flow is going to be on this well. So if you're going to have a bottom hole pressure, flowing pressure, and a 7-inch or 5.5-inch completion, how much grease can you advise your production vice president or your exploration vice president based on the information that you produce from the waterline model? Right now, all they're asking is it going to burn? But if you can tell them what the final result might be with some uncertainty, you'll probably get promoted. And that's all I have. I'll leave that part of it up, and I guess that you can turn the mic over to everybody else. And I'll shut up. How do I do that? I'll mute myself. If I can figure out how to do it. I will mute.
Okay.
Hello.
Hello. Thank you, Mr. Chris. So this is a very great presentations, very complex mathematics, and very interesting to be discussed. So we have several questions from our audience. So I think I will let the audience directly ask the questions. I give to Ramadan Ibnu to unmute your microphones, and please directly give a questions, because the questions that you write in the chat is not really clear for me. It's better for you to directly give a question to Charles.
Okay, thank you, Mr. Moderator. So before I ask, could you give me a permission to giving 2 questions to Mr. Charles?
Yeah, sure.
Okay. So, Mr. Charles, by the way, it was a great talk and it's a nice presentation. So I got two questions. What I want to ask is, the first one is, can a PASM be classified based on petrophysical properties other than the geological properties? What I mean is, if mudstone overlap with sand and the porosities that favor production overlap the vertical boundaries, in this case, the reservoir will be the same. and will also include the mudstone, assuming it has movable hydrocarbons. If yes, what does this mean for the GRV and NTG, or as known as net to gross? And the second one is, what can be appropriate workflow for the study of diagenesis and reservoir quality in deeply buried sandstones if petrophysics is incorporated? Thank you. Is it clear?
Mr. Chris, is it clear for the questions? You can directly answer the questions. Hello, Mr. Chris. Can you unmute your microphone?
Okay, there, I'm unmuted. I believe the first question had to do with GRV, but now I realize you guys are embedded shaly sand kind of environment people. A well bore is whether it's vertical, horizontal, or slanted, is just a snapshot at the total three-dimensional volume hydrocarbon reservoir distribution that you've got. So that's a 6-inch or 8-inch view of the world. And so your challenge as a geomodeler is to be able to go from those basic pieces of information out hundreds, if not thousands of feet, meters away from that particular wellbore, controlled probably based on your seismic and maybe some wireline image information. Yeah, that's probably a question that's probably best answered by a really good geomodeler. I know of one. Tim Salter. I can put you in touch with him. He'd probably have a very good opinion on that. But, you need to be able to, if you've got a bimodal system where you're dealing with sands and you're dealing with mudstones, or the mudstones might be your lamina, your shale lamina. So you basically have a bimodal system. So it's how much net pay that you have and how laterally contiguous you expect that net to gross to be. If you're going to be dealing with channels, crevasse plays, you're going to have problems. You're going to have to do a significant integration, because once you change depositional environment, you're going to have, your numbers are going to change. Your second question, I believe, had to do with what recommendations I would have for looking into diagenetic studies, maybe from the core measurement side. Is that what you mean? Core and/or log? Okay, if we're talking about doing diagenetic studies, petrography is going to be very high in there, and I would want thin sections. I'd want to know what's my distribution of clays. Have I altered the rocks? A lot of the sandstones that I have worked with in the Far East are cosic. So the higher the temperature, the more feldspar dissolution you're going to have, and redistribution of clay precursors. So one of the other things that you're going to have to be able to do is do a basin model reconstruction and geothermal reconstruction, so that you can understand how long you've cooked that rock. So the best place that's going to start is acquiring samples in some of your organic intervals so that you can do your I'm brain dead. What do we call that? Basically, would be doing the same kind of work that you'd be doing for a resource play. Well, you need to know where your flows are in your core system.
Okay, I hope the answer is from Mr. Chris can answer the questions. We have another questions from different audience, but before I read the questions, I also have a question to Mr. Chris regarding your works. If I'm not wrong, that when you starting with fractional flow determination, you start with the MICP permeability and porosity characterization by using the machine learning. So actually, what is the main purpose you using the machine learning? In here, is it not enough to create the classification only based on the general rock types?
Oh, okay. The machine learning is done in two parts. The first part is machine learning specifically against porosity, measured core porosity, core permeability, and to deconvolve the mercury experiment into how many modes, how many pore system modes do you have, what is the entry pressure, bulk volume, and shape factor for each of the up to 3 modes of porosity. So that you could have 10 variables determined from the deconvolution. 3 BVs, 3 PDs, 3 Gs, and an N, or the number of the mode. And so with the next machine learning bit, you're entering in and you're doing the saturation height using Gaussian process regression to look at your porosity, your input porosity, input perm, your TVD, your free water level, your hydrocarbon and brine densities, to predict, basically find what is the best solution at each depth level for the probability that a single, bimodal, or trimodal, and what would be the amount of hydrocarbons in each of the 1, 2, or 3 pore systems. And then the second part of that is doing the land so that you can back into what SW is and what SO is, and then enter into Buckley-Leverett to come out with a fractional flow. And you compare that fractional flow to what you got in your sampling, and you make an iteration to where you go up or go down to put more buoyancy into your system. And so at the end of the day, you want the fractional flow to best match from the sampling to the model results. And what we typically find when people are picking contacts, and they're doing it from RFT, MDT, RCI, what have you, the uncertainty in an oil reservoir is about plus or minus 30 to 50 feet to try to run delta rho GH and tie where the water and the oil gradients intersect for a function of accuracy. Whereas with the full physics model, you got it down between 1 and 3 feet. Now, that's why a lot of people do their gradient testing only in gas wells, because you have significantly higher buoyancy in gas wells.
All right, Chris, it's very interesting, but in case in our real cases, we don't have a ton of data that you have a very complex data. But for when we have a very limited data just for the logs, for example, and with the NMR, is it enough to answering the water saturation problem in low resistivity?
If you're dealing with micrites and chalks, definitely. You can, these assumptions that you made, if you're under 10 millidarcies, 10 or 20 millidarcies or less, carbonate, micrite. And some of your miocene carbonates may be micritic, but most of your miocene carbonates are bioclastic. Bioclasts are easy. It's the micrites where you're going to get the false negatives. That's where you leave reserves in the ground and you put cement in the hole. What we don't want you to do is plug a producing interval and have somebody come in, the Chinese behind you, and dig an offset to your acreage and find a new field. So if you're dealing with carbonates or micrites or chalks, you can make a very good approximation based on NMR and NMR resistivity and sampling. And that fits very nicely into the let's go cheap drilling philosophy for vertical and horizontal offshore wells to save cost. But I would highly suggest that it's a nice thing to do, especially in a rank wildcat, to go run some wireline, get some wireline plugs from rotary sidewalls so you can kind of characterize your rocks. Now, if you're in laminated shaly sands, the NMR is not going to do you a whole lot of good because it's got about 4-foot vertical resolution. You know, Schlumberger tried to sell you a CMR piece of garbage, but that's fine. Let them go ahead.
Okay,
How about mTOR?
Okay, thank you, Chris. So I will throw to the audience again. We have another question from Eko Nur Saputro. Are you here? If you because I'm not really understand your question in the chat box, so could you please unmute your microphone and directly ask to Charles? Eko Nur?
I'm still here. Go ahead.
Eko Nur, are you here? Can you directly ask a question? Okay, no response. We go to the other questions from Wilson Supriyadi. For the high temperatures environment like oil-based mud, will NMR work properly? How do we get the T2 values? And also, can we use NMR to determine fluid types on unconsolidated sandstone reservoir? Thank you.
Okay, number one, if somebody sells you an NMR and oil-based mud, I got some swampland in Florida you can buy. It's useless. You have to do fluid substitution to get the oil signature out of the NMR, and you wasted your money.
Okay.
So your hose, high temperatures.
The second question, can we use NMR to determine fluid type on unconsolidated sandstone reservoir?
Fluid type, between water and oil or water, oil, and gas?
Maybe 3 of them.
Unconsolidated sandstones, I'd be a little uncomfortable there. The biggest problem with the unconsolidated sandstones is if it's unconsolidated and say you're in a channel sand, which can be fairly coarsely grained, and there's a pretty good relationship between pore body size and pore throat size. That would be the kind of relationship that we would try to use with NMR. Now, in an unconsolidated sandstone, you can very, very easily be pressure supported, so that if you were to bring that rock back to surface, you'd actually see some significant loss in porosity once you lose the fluids from the sample. So you may not accurately characterize the porosity. And that's where I would prefer, if you're going to be in unconsolidated sandstone, that I would have, number one, I'd have an NMR and a mandrel NMR tool, and number two, I'd have a density for sure.
Okay.
And between the density and the NMR, you can do DMR gas and kind of get a good idea of what your fluids are from that. And if you got a neutron in there, you kind of get a sniff of whether you've got light hydrocarbons in there, but you might also be able to see that on the NMR. And I'd want to have samples because I'd sure like to know, or at least pressures and/or samples. I'd sure like to know what the PC is of that reservoir.
All right. Okay. We have another question from Ahmad Rashid. The question is, in the best practice, I mean, if we only have the conventional logs, what is the best practice equation to calculate water saturation for low resistivity PE, either in carbonate or shelly sand?
Okay, I won't touch the saline sands right off, but for carbonates, I would go with Archie. One of your challenges in your carbonate is what am I in a carbonate play? You're not going to have, or you shouldn't have, associated clays unless they're orthogenic. So you don't need a Seaman-Dew equation. You don't need any saturation modifying component due to clay. That's not there. So, the place that I would start is Archie2. Archie equals M equals N equals 2 is where I would start. If I know that if I'm dealing with porosities that might be in excess of 20% porosity, the first thing that I might do is I might modify the cementation exponent and use the Bori equation, which will tend to cause M to increase as porosity increases. And when you get into the low porosities, it'll actually drive cementation exponent below 2 when you get into your denses. Now, until somebody tells me how you can, in a carbonate reservoir, accurately measure imbibition or measure RI within your lifetime from in a carbonate, you're best off to stay with a saturation exponent of 2. That being said, if you're in a highly macritic rock, you're going to find that the saturation exponent is actually linear from 100% saturation to about 60% SW. And then once you get under 60% XW, it's going to bend to the left. RI is going to bend to the left, and your saturation exponent is going to drop. If you're dealing with non-asphaltic oil and very little dolomite in your carbonate reservoir, you're going to have the highest probability of being profoundly water wet. So you're going to have a fairly neutral saturation exponent. So that SWN equals 2. Now, if you've got dolomite or if you've got asphaltenes, precursors in your oil, or you have a tar mat, you got all the conditions for having mixed wetting conditions to oil wet.
Okay. Got it.
And I avoided your sandstones like the plague, because you don't have aeolian sandstones in this part, in your part of the world. They're mainly volcanoclastic fluvials and river systems and marine systems. So they're all reworked. You got clays coming in and low energy environments. So you've got to handle the clay situation first.
All right. So another question is from Mohlis. What is the constraint, if any, of utilizing NMR in a poor quality reservoir?
I personally don't like NMR under about 5 porosity.
Okay. Okay.
Diminishing value. For me, I'd have a density neutron in there, but we got people that are allergic to nukes.
Mm-hmm. Okay. So another question from Mas Cahyo Nugroho. What would be the resistivity cutoff to enable low resistivity pay NMR saturation derived?
I mean, how low can you go? Those examples that I showed you from the Middle East, in those intervals that were full of oil, the raw log resistivity was in the depth crack, below 0.2 ohms.
Mm-hmm.
SW in those cases was in the neighborhood of about 20%. Highly function of saturation height. Once you started putting oil in that rock, once you went 75 feet through the column, whoop, you're in single digits. And where's resistivity? It's in the depth crack. So tell me your answer. When people looked at the logs, they said, up ocean, put cement to it, and somebody was dumb enough to perforate it and flood drywall. 1.8 billion barrels of low resistivity pay in the NEB, Northeast BAB unit in Abu Dhabi, in the Thamama A. I haven't discovered a billion barrel oil field in a few years.
So, okay. So we have another several questions. It's coming from Faris Khidir. The question is, does the Buckley life rate function hold for the pore system?
Bucket levery, all you're basically doing is mixing viscosities and perms. What's your viscosity of brine? What's your viscosity of oil? And what's your relative perm to oil and relative perm to water? And you're mixing it and coming up with a fractional flow. So the applicability is a function of what you're driving your relative permeability curve is, and we're basically because we want an analytical solution, we're basically using Corey exponents.
Mr. Faris Khidir, do you want to ask more something, or you can unmute your microphone, please? If it's already clear, okay, I will continue to the other question.
Hello, do you hear me? Hello.
Hello, Ferris. How you doing, Bubba?
I'm fine, Chris. Okay, with regard to your answer, I'm almost satisfied. Just like maybe because I mistyped it. Actually, I want to ask, like, if it does hold for all the different type of pore systems.
Pore system 1, 2, and 3. Most of your fluid flow is going to be conveyed through your largest pore system. All your fluid transport in your pore system is going to be in the primary pore system. So whichever your best one is, that's where the fluids are moving from point A to point B. So it's pore system number 1 is what matters.
Okay. you, Chris.
Yeah.
Appreciate it.
The next questions will be from Mr. Dwi Kurniawan Said. It's a bit long, but I will give the chance directly for Mr. Dwi. You can unmute your microphone and you can ask directly to Chris.
Okay, thank you, Akbar. Hello, Chris.
Welcome.
It's me, Dwi.
G'day. Ask away, lad.
Yeah, I've got the question for you. First, what is your calibration reference for the SW?
Primary calibration reference for me is Dean Stark. Dean Stark.
Oh, okay, great.
Properly obtained Dean Stark.
Okay, great. And for the second, for this micrite, do they relate to particular depositional environment, or maybe all of the carbonate environment will be micritization, will have a micrite?
Almost every carbonate environment has a component of micrite. Anytime aragonite is dissolved off of shells, it precipitates as micrite. But pelagic micrite is very, very common, and it will be pronounced in very low energy environments. So it'll be pelagic deposition. So it'll be below the fair weather wave base. Your carbonate factory, which is usually in the photosphere, photozone, will be warm water. Once it gets, that warm water gets below the thermocline, then you will start dropping out or precipitating calcium carbonate. And it'll start raining on the seafloor as micrite. That's why all of these grains, micritic grains, are typically nearly the same size. Now you can have positive or negative diagenesis post-deposition, in that you might have some porosity enhancement when warm water goes through there, or lower pH water goes through the rock and actually dissolves some of those crystals away. Or you can deposit sparry calcite to cement some of that micrite up. And that's why you, in the Guar poro-perm interval, you saw the micrite line was fairly straight, and then once you got under about 5% porosity, it fell down by a couple orders of magnitude, and this is because of sparry calcite cementation, destructive diagenesis.
Okay, thanks, Chris, for your answer. It's very clear for me.
Okay.
So thank you, Mr. Dwi, for the questions, and Mr. Chris for the answers. We have the last question, I think, from Mr. Yulianto Yong. Mr. Yulianto, it's better directly you give the questions. You can unmute your microphone.
Hello, Chris. This is Yulianto speaking from Balikpapan.
Hey, how are you doing?
Fine.
Former Unical property. I remember when it was Unical.
Yeah.
I ran hash out there.
Okay. So I have a question about the wettability.
Okay.
So according to you, your experience working in the Middle East, so most of the carbonate reservoir tends to be water wet or oil wet or mixed?
In the Middle East, from as defined by relative permeability, almost all carbonate reservoirs are the way to go.
Okay.
But but a lot of these reservoirs have asphaltic precursors in them.
But if you have the micrite.
Yep.
According to you, if you have the oil-bearing micrite, is more to water wet or oil wet?
Water wet.
Water wet.
Water wet. Now, where does that matter? it matters for your arch equation, what's your saturation exponent you're going to play with. The second place where it really matters is the T cosine theta, your interfacial tension times cosine theta. Now, Jan Bunting, and I can't remember, I've got his email, so if you were to ask me this question, I could pass it on to him. Saudi Aramco spent a lot of money getting a correlation between hydrocarbon composition and interfacial tension cosine theta, because it's the product of interfacial tension times cosine of the contact angle that is used in the Purcell equation to convert between laboratory conditions and reservoir conditions. Now, the interesting thing is if you're strongly oil wet, that product is about 4. If you listen to the core service companies, they'll tell you that product for carbonate is 30 and 30, which comes out to about 25 and change. What we found out in the Middle East, that we haven't seen any numbers higher than about 19. So the range of interfacial tension contact angles goes between 4 for oil wet to about 19 for strongly water wet. And most of the reservoirs that I deal with in the Middle East, I vary from about 13, 14 to maybe 17. And I will use uncertainty applied to that parameter selection so that I can look at how much influence that has on my output solutions.
Okay. No, because I'm thinking about the value of the RC saturation exponent, because as far I know that between water wet and oil wet, the N value will be different.
Oh yeah. You can be from below 2 for water wet to 5 or 6 for strongly oil wet. Now, there's a good paper on oil wet reservoirs by, shoot. I think of his name here in a minute. Rajasthan Field, Terrence O'Sullivan, I believe, had his, Terry O'Sullivan had his name on the paper, and Ron Zittel talked about oil wet rocks in Rajasthan. And these guys would flow water at 2% SW.
Okay.
The rock loved the oil that much. And then Asbjørn Gulliksen, and I want to say it was 2007, wrote a low resistivity paper for carbonates where he actually shows you some RI experiments which have a bend in them in the thermometer, which says that because of where the hydrocarbon is in the rock, when when you do a drainage RI, you are oil saturation is increasing. So you're doing the experiment, you're driving oil into smaller and smaller pores in the experiment. And when that happens, you lose the conductivity to water. And so you see the RI change dramatically once you get below 60% SW. And so you have a nonlinear response for your saturation exponent. Saturation exponent is a function of column height. And that's really going to bend your mind a bit.
Okay.
But basically you do a risk analysis. Okay, what's my best case? What's my worst case of these parameters? And run it, do your crystal ball, and what's your probability density function, not of SW. Your probability density function is on SO. What's the uncertainty in my oil volume?
not just the ratio of oil to water.
Hello?
Yeah, I'm still here. I'm done.
Okay. Yeah. So my last question.
Sure.
Okay, Chris. So as you know, the resistivity index or RI, in fact, is the sequential measurement from the formation factor.
Well,
So after,
RI is different than formation factor. Formation factor, you're only dealing with the brine, the resistivity of the brine in that's 100% brine saturated at formation temperature. Whereas in the RI experiment, you start there with a fully saturated piece of rock and you slowly introduce hydrocarbons into it.
So according to you, is it possible to have the N value less than the M value?
Oh yeah. Oh yeah.
In such case, for example, do you
Can
have
easily
any?
happen. As a matter of fact, you're expecting to see M saturation exponent. I'm sorry, your cementation exponent to be a single value, whereas the saturation exponent N Nancy can actually be a function of capillary pressure. It may not be constant. And if you send me an email, I'll send you back a copy of Asbjorn Gullick's paper and show you the, or you could look at my paper that was referenced on the second or third slide. It's got, I believe it's got a copy of that saturation or that RI experiment.
Okay, I will send you the email because it's interesting for me.
Okay.
Yeah, many thanks.
All righty. I'm doing nothing except playing golf tomorrow morning at 8 o'clock.
Okay, thank you.
Thank you, Pak Julianto, for the questions and the discussion. We have a new question again from Ahmad Rashid.
Okay.
Ahmad Rashid, can you directly ask the question, please?
Hello, Mr. Chris.
Hello, how are you again?
Yeah, fine, sir. And just a last question about the Archie equation. Sometimes doesn't work properly in development wells. As you know, we have some depression, maybe oil and gas with some oil pulses, something like that. In some cases, when we calculated in sandstone conventional reservoir from Archie equation, we didn't get the water saturation estimated accurately. And this is tricky, especially in development well. So what is your opinion, and what is you recommend to calculate the water saturation to get proper value in development well to get very good value? Thank you.
Okay, I believe, let me rephrase your question and see if I capture the thought. I'm assuming you have Dean Stark's, that you're putting hand on heart and saying that Dean Stark saturation is correct from exploration wells. And then when you go to development wells, and this is for shaly sandstone reservoirs, you're coming up with not what you think is the correct answer. Is that for water saturation? Is that an accurate assessment?
Sorry, I mean about for sand reservoir, not shaly sand.
Sand. Clean quartz
sand.
Okay,
yeah,
sandstone reservoir. Now,
clean sand reservoir.
Okay, now a lot of the sandstone reservoirs that I've worked with in Australia up through China and west of India, these sandstones are arkose. So they've got feldspar content. So
you need to be able to characterize the feldspar. You also need to have a handle on whether or not you have any porosity enhancement or positive constructive diagenesis where you have created porosity by dissolving out some of the feldspar grains. Now, when the feldspar grains dissolve, as the fluids move around in a reservoir, it will precipitate clay precursors. And if you're precipitating out illite, you can actually have the illite block pore throats and pore systems. In a project that I worked on in Indonesia a couple of years back, we had only 14 mercury tests that I could remember, and almost every single mercury test were bimodal, indicating that there was a primary pore system at play and a secondary pore system that had nothing to do with the sand, with any clay content in the sand. It had to do with all the fluid transport would take place in the primary pore system, and your secondary pore system had no hydrocarbons in it, and we're not participating in transport.
Okay, but just about when you run resistivity from triple comb, for example, you see some decreasing in resistivity from the original well, in exploratory well. So the difference between the original value from resistivity and the value from the development well will be some kind of depletion. Okay, and when you get the production from this development well, you see different oil potentiality from the production, different than the resistivity that you are seeing it in triple comb. It's different because we have some kind of depletion, but this depletion may be gas or maybe pressure decreasing only without gas. This is a tricky. I cannot discriminate.
So the only place that you're gonna,
yeah.
If your resistivity is lowering, that means that your pore volume is either got higher temperature brine in it or more brine and less hydrocarbon. Now, you can, if you, are you producing with the water cut? It's not really fair to compare it back to the original exploration well that could have been producing above the critical water saturation, where you have no production of water at all. If you're above the top of the transition zone, or if if you're actually on the imbibition curve, you can have movable water. You've imbibed water into the oil column.
Yeah, okay.
So that's another thing that that full physics model tries to predict based on land. So you got an idea how well contained your seal is.
Okay, thank you.
Okay.
Thank you for the question. So the participants, maybe I missed some of the question. If in the chat box, you can directly ask here. You can unmute your microphone and directly ask to Charles. No question?
Yes,
so, yes, Mohlis?
Yeah, this is from Jakarta.
All right.
Yes, I just want to reconfirm from the answer for my previous question. As Chris mentioned that for the poor quality reservoir, we actually do not recommend to use NMR. Is that correct? Chris?
I'm not a real fan of NMRs below about 4 or 5 PU. Now, I have been known to run them in resource plays where the true porosity is not going to be very high. If it's going to have light hydrocarbons in it, you're going to have a problem.
Okay.
Because you'll underestimate the porosity with light hydrocarbons.
So you recommend to use density neutron instead?
Yeah, if I'm dealing in a sand, as long as you can get a round borehole, that's a critical thing. Number one, a round borehole. I love density log.
Okay.
It's density neutron if I'm trying to do some hydrocarbon typing or maybe even some shaly sand work. That's good. Very few people are running wireline anymore. So most of the stuff you're having to get is LWD. If you're in poor quality rock, you may also see an advantage to having image logs in as a substitute for and unfortunately, there is no such thing as a good acoustic tool for LWD, especially if you're going to do geomechanics. Can't get a shear on pipe.
Yes, thank you. It's clear to me then. Thank you.
Okay, Mr. Chris, you already answered all of the questions. It's a very much.
I have one question. Chris,
okay.
Assuming we are dealing with fracture carbonate when the porosity is lower than 5 PU, so this methodology is not working. Just want to get confirmation from you.
Are you running wireline or LWD?
It's running LWD and wireline, both.
You're running both. I would highly encourage, number one, that you have a good cross dipole. Image logs and cross dipole are going to be immensely helpful for you to understand it. And because you're also going to need a density with that so that you can do your geomechanics. But if you got a fractured reservoir, you're going to have problems getting around the borehole. And you need to have a good conversation with your structural geologist to understand the impact of doing the structural reconstruction and take those fracture systems out of it, unless you're just dealing with thrust faults.
Okay, thanks, Chris.
That answer your question? NMR in fracture reservoir, it's like needle in a haystack. Because remember, you got 3 or 4 feet of vertical resolution with your NMR, and your fracture aperture is 100,000th of an inch. Gee whiz. Now, what nobody's talked about here is advanced mud logging, gas chromatography, and looking. Talk to a guy by the name of Mike Smith with AHS. You can find him on LinkedIn. He can help in that kind of reservoir. He can make you some money.
Okay, got the point. Thanks.
All right.
Okay. So we still have a time actually for 20 minutes, but if nobody gave a question, maybe we can end it the discussion today. I think Ghazali unmute the microphone. Do you have a question, Ghazali?
Oh yeah. Sorry, I'm sorry. I'm very late to the party, but right now I'm working on. I'm not a petrophysicist, by the way. I'm working on some basement fracture reservoirs for the Cairo in Cairo. So basically what we have here is like, what do you think about the water saturations would be in the basement? What kind of like irreducible water that could be over there could be very low, or is that something like it's more oil wet or water wet? And then what we have here, what I think is a bit funny, we have like larger reservoirs in the carbonates. The carbonate water or the irreducible is about 25%, so it's basically 0.25. But then the sandstone reservoirs is 0.15. So in this case, like the carbonate is more water wet compared to the sandstones. What do you think about it? Is it? By the way, that's coming from skull measurements, but not that many in terms of population, so it might not be that representative. I'm not really sure.
Okay, I've seen a lot of oil wet sandstones, and most of the carbonates I've seen have been mixed wet to slightly mixed wet. Now, let's talk about your basement place. Is this Vietnam?
No, it's in Cairo. So it's
Cairo, Egypt.
Yeah, Cairo for Egypt. So this is kind of like they outsource some of the modeling works to us in Kuala Lumpur, but we're not really that familiar with geology in Cairo, so we're kind of like a bit blind here.
Okay, I've worked basement plays. I've worked volcanics, intrusives, and granitics.
Yeah,
your biggest problem is going to come up with, how do I compute porosity correctly? Screw water saturation. You got to get porosity right. NMR was always my hope in the plutonics, because you could have andesites or different types of lavas. Now, granites are hornblende, mica, feldspar, and quartz. So, and the percentages can change inch per inch. And it's whether it's a dog's breakfast. And coming up with porosity in basement plays, I mean, non-plastic or non-carbonate plays, that's a problem. And most of them haven't made the correct measurements to be able to minimize the uncertainty that you might have.
Yes. So what we have here is about like a granitic basement and basement wash, some metasediments. So what they have here is how they calculate porosity by using some image logs. So they have interpretations on image logs. They have the density of the fractures. I mean, some approximation of the apertures, and then they calculate using sort of windows to average how much is the fractures over half a meter, how big is the opening, something like that. But of course, how do we match 40 years of history is a bit tricky. So what they did is like they ran batch of proxy-based assisted history match using enables, run hundreds of realizations with lots of multipliers and so on. So yeah, I mean, the uncertainty is big.
Well, they've been smoking stuff that came out of Amsterdam. There are some things that they could experimentally do with ester studies, where they could inject different alcohols into the reservoir and measure the result and producing it back. Because if you can't get the pore volume right, then so what? If you're working with what's your uncertainty on water saturation? So the uncertainty in your answer is basically the magnitude of the answer. So there are, you got to get the pore volume right first. If they've got core, you can do some core measurements to actually see whether or not you're able to introduce a hydrocarbon into the matrix component. Fractures are going to they're going to fill up very easily, but the fractures don't contribute diddly to the pore volume.
What's the average like ballpark, or just basically numbers that people usually use for the fracture reservoirs? Is it like 1%, 2%? We probably have like about 2% in average in terms of static modeling that they have. They calculate, it's probably 2%. Don't really know.
The best person in the world to answer that question is a guy by the name of Ron Nelson.
Yeah, I saw that book.
Yeah. And most of the fractured reservoir plays are they do 1%, 2%, 2.5% uncertain. And they basically make themselves a PDF.
Yeah.
But Ron Nelson, he still answers the phone. I think he's still alive. He worked with me in Amoco too.
See.
A lot like Mike Smith. Mike Smith, for those people listening, mud logging and gas chromatography is basically free. And there is no better scientist in the world than Mike Smith. And he will find you guys grease.
All right. Ghazali. Yeah, I know your reservoir is complicated. Yeah. But yeah. We will discuss more. Maybe we will invite another speakers who can speak more details in the basement fractures. So it will be input for SPE Java session in ISPG. It will be nice discussion as well for the next meeting with the fractured basement reservoir.
Yeah.
So
thanks.
I think we almost say at the end of the meeting today. So I think, Mas Julianta, can we end the discussion today?
Yeah, I think this is a good talk, good sharing from Chris. Just to remind for the evaluation form that already shared in the chat box to all participants, can you please fill up for our evaluation and improvement?
I don't know how long I talked, but I probably talked more than an hour, and for that I apologize.
Yeah, and maybe Chris, you can summarize your talk at least as a takeaway message to all the participants tonight in Indonesia time or in other region time, please.
Okay, you want me to answer the question now? Or do you want me to write you something?
Yeah, just a takeaway, couple of sentences was basically the important to understand the multi-phase flow petrophysics.
Okay. Multi-phase flow petrophysics. Number one, we're highly basing this on rock information. That's where you're going to get the absolute best response. If you're the multi-phase flow petrophysics, which has a database of MICP, which is characterized, deconvolved using our Thopal software. Oliver Monkey developed the Thopal software. We characterize that. The deep machine learning allows you to handle unimodal, bimodal,
of trimodal pore systems that can either be in sandstones or they can be in carbonates. Very often in Julianta, most of our sandstone plugs from the field that we played with were bimodal. Only a couple unimodal. So this technique would have worked in that reservoir. We need to know fluid properties, the viscosity, the brine, the viscosity of your oil, the interfacial tension. We can approximate it when we risk it. And if you combine it with, at the time of the digging the well, if you're doing fluid sampling, we can get a very accurate handle on where the fluid contact is. Not the oil down to, or the production of oil down to, but we can get where free water level is. And it may actually be tilted in your reservoirs. The second thing that you do is most people that are doing saturation height work stop with getting porosity, permeability, and that stuff. That's it. That's in the game for them. We take it that step further by going and integrating in relative permeability to get fractional flow and minimizing the risk and uncertainty of the fluid contact. Now, what can come from this is the ability to actually predict rate. From the responses that you get from multi-phase petrophysics, you could back predict, you could forward model what you should expect from your production logs. And if your production log does not match the model, could be a problem with your completion. Add to it nodal analysis and to sort out what kind of tubular string that I need to run based on what delta P. So you can actually start doing some more sophisticated modeling, performance modeling for managing your completions. So you're integrating the loop of understanding porosity and permeability, determining a more accurate water saturation, screw saturation, oil saturation, and then being able to tie that to relative permeability. So what is relative permeability to water? What's relative permeability to oil? And what fluid would you expect to flow, whether you are in drainage or in imbibition? So you're taking it one more step. I mean, first step in common log analysis is just porosity and water saturation. When somebody does a term equation and you got porosity, water saturation, term, give it to the engineer. And we're trying to have the engineer be your best friend.
Okay. Yeah.
Certainly confusing, right?
Yeah, but at least now we get more understanding about this new approach.
I think you find it's pretty bloody good. If you're wanting more information about the blood and guts and details, send a note to Mr. Nicholas Lesueur at bakerhughes.com. He's very, very brilliant Frenchman. He speaks pretty good English. Interesting accent.
Okay, so Chris, on behalf of SPE, Java, and ISPG, I would like to say thanks for your willingness to share this approach, the multi-phase flow petrophysics. Hopefully all the participants today can get this knowledge and can be applied in their actual work. And to all participants, thanks for joining this session. until late. And hopefully you can fill up all the evaluation form. And this records video will be published in the SPE Java YouTube channel later on. Again, thanks to Mas Akbar as a moderator today, and Chris for your willingness to share. And last but not least, this is a good time for us to open the video so we can have a picture time together.
There you go. You're not going to get a picture of me. I'm a white-haired old guy. I don't have a camera on this computer.
Yeah. To all participants, can you show the video? Mas
Well,
Akbar,
I really want to thank all the people who came to listen to me talk, and I thank the society for giving me a platform to speak from. This is a subject that's near and dear to my heart. I'd like to see more people doing this. I think it's not that expensive. It's really fast to do. And
yeah. Chris,
I see the advantage of it actually tied into operations to get the right data we need.
Okay, thanks. Can you stop sharing, Chris, so we can have all the participant face?
There you go. It's all yours.
Okay. So in the first page.
Jul, mana Jul? Oh ya.
Jempolnya dong.
Jempol, jempol semua. Jempol, be ready ya.
Satu, dua, tiga. Oke.
Oke, patch kedua.
Bang Jul yang screenshot ya?
Iya, saya screenshot.
Alright.
Jul, udah ada semua belum Jul?
Oke.
Aduh, kenapa sih Dwi sih?
Apa sih Pak Gede?
So, okay, everybody, we have all the picture. Again, thanks for your attendance. So, just a gentle reminder, tomorrow we have a low resistivity pay at the same time, at 8 p.m. Jakarta time. So, if you want to join, please register yourself in the link already published in the WhatsApp or in the LinkedIn. So we can have a session together tomorrow with Mr. Kokoki. The topic about low resistivity pay in plastic reservoir. Again, thanks Chris, thanks all participants, and thanks to the SPE. Please renew your membership to get full benefit of a member. Good evening. See you guys.
Thank you Bang Jul.
Terima kasih Mas. Terima kasih.
Thank you Akbar.
Thank you Akbar.